Hello everyone, I'm Nikhil. I think the intros have been great. No need to reiterate. So we're talking about Chronon, Airbnb's feature engineering framework. So there are two terms in the industry: the feature store and the feature engineering framework, and probably also go into why there is a difference and what are the main differences. So some announcements. So this used to be called Zipline. If you saw, the title used to be Zipline, and now it's changed to Chronon. Do not worry, you're in the right place. Right. And currently we are doing a private beta. So we have been working with a few companies to uh, install, set up Chronon and get some feedback and finalize on the API more or less. Right. So if you're interested, drop a mail to either me or my manager. Cool. With that, let's get started. So this is the team behind Chronon. So it's not just my work. I want to thank all of these folks, wonderful folks that have worked with me in the last few years to bring this to light. So the agenda is really simple. So what's a feature platform and how do you use one? Right. So to understand a feature platform, we need to take a step back and see what are the big pieces in the ML workflow. So the simplistic view is that there is some training data. You generate some generate a model based on the training data, for model training, and then they use it. Then you use it for inference, either online or offline. Right. So this, I call this the Kaggle view. There's a lot that happens behind the scenes to like get this view to keep churning. So you need some features offline and labels offline, and you join them to generate training data. And for online inference, you need features to be served online. Right. So all of that comes from raw data that already exists in your company or data that you have access to. So the job of the feature platform is to drive all the red arrows. I don't know if you can see clearly, but there is these red arrows, and then there's like black arrows that are not bolded. Now the job of the feature platform is to take raw data, generate features and labels for training data, and also serve them online for inference. So it's a lot of compute heavy work, essentially. Right. So just walking through these arrows. So there is feature backfill. So you look at raw data and backfill features. So if you have a feature idea, let's say you want to use user clicks in the last 5 minutes on a category of items, if you're serving e-commerce site like Amazon, right? So you'd want to backfill that feature to generate training data, right? And then you extract labels. Like let's say you're serving a recommendation model, the label would be click. So did the user click or purchase? Right? And then you put those two things together and generate training data, right? That's the label join. And once you are okay with the trained model, you want to serve features. So you want to refresh features online, either through real-time pipelines or in a batch pattern, and then you serve them for inference. Right. So this is roughly what I'm talking about when I say feature platform. And last but not the least, we also want to log all the features that are being served for two purposes. So if a feature is already online and if you log it for enough time, there's no need to recompute and rebackfill. So feature logging is a dual of like feature backfill. So you can either backfill from raw data or like use the log feature data. And once a feature is fairly stable, there's like no need to backfill it. You can just like derive it from logs. Right. So the goals of feature platform, the first one is management. So what I mean by that is there is one unified API to drive all the red arrows that I was talking about. Right. That manage also to manage feature lifecycle. So how do you author and how do you release? How do you change a feature? How do you add a feature to your feature set? All of that like goes into authoring and release. And the last but not the least thing is feature observability. So in the previous diagram, I didn't like show any box or an arrow related to any feature observability because it is cross-cutting. So at every transformation step, we need to understand what's the input data like, what's the output data like, and we need to use that to guide us in like what features to choose or if the input data is good enough. So there is roughly three pillars of feature observability. First one is training data quality. So you do the feature backfill or get different logs, get some labels and join them and create a training set. You want to know if this data has coverage, if the distributions look good, or if there is correlation between any two things so that you can reduce the size of your feature set. So all of that comes into training data quality. This all happens before you even serve an inference request. And the next thing is feature drift. So once you begin serving inference requests, what happens over time is the data changes or there is issues upstream from the data sources that feed data into features. And as that those pipelines keep changing and as the real world data distribution keeps changing, you want to make sure that your model understands the new data. If it doesn't, you want to know upfront that there is drift in features. Right. And the last thing is online offline consistency. So before I explain what that is, I would just want to say that it's one of the biggest reasons why machine learning projects fail, which is that you train a model, it performs wonderfully offline, right? And once you begin serving it online and observing performance, it doesn't match up, and that kills a lot of machine learning projects. It's like you spend a ton of effort into doing a lot of work offline, and when you like try to use it online, it just does not materialize. So what causes that problem is that the data that you have trained with offline and the data that you're using online are different. So one thing that we want to guarantee here is that the data that is offline and online are both consistent. They're coming from the same distributions, using the same computation logic in both cases. Right. So let's talk about the API. Right. There is a lot of moving parts in that flywheel, and we want to simplify all of this for the user essentially. And one way to do that is to provide a powerful API that is simple to use and familiar, right? So one principle behind Zipline API, I'm going to show you like what the API actually looks like. But the guiding principle is that we want to build these Lego blocks, give you the Lego blocks so that you can assemble your feature pipelines however you want to very easily. All right. So by power, I mean a few things. So there is no real understanding of the source type. We'll see what kind of sources exist, but there is, you might be familiar with the star schemas, fact tables or dim tables, or like event data or like database snapshots. There is various kinds of data sources. There is change data too. All right. Those are not very explicitly modeled in relational algebra or like in SQL. So what we want to do is add those concepts as first class events. So you can just say, okay, this is a database snapshot, or this is change data, or this is just events, right? And we can use that to derive features for you, right? We have different types. I'll like show you examples later on. And the next building block is group by. So this is the thing that actually does the computation. It takes your raw data, understands the source type, you can express filtering and transformation here and specify aggregation, right? So the aggregation inside group bias is a bit more powerful than what SQL supports. They support time windowing. And the big reason here is that time is not a first class citizen in SQL. Right? If there are two relations and if you are trying to say that this relation and that relation have a single timeline, right? You can order the events based on that timeline. That is really not a concept that SQL understands, right? So that's why we have to extend it to make it powerful enough for feature engineering, right? And the last one is join. So because we know that different relations can have the same timeline, we can do a temporal join or a point in time join. So you can get feature values at various historical points in time. Right? And then there is the last concept is like staging query. So we are going to go into a bit more detail on like one of the more complex concepts. But the last one is staging query. You can put arbitrary ETL queries into this concept, into this API, and it will execute that for you. One downside is that this will not be real time. This will not be point in time correct when you try to batch. This will only be batch correct. Right. So you only use this when the complexity of what you want to express is beyond what group by or join can handle. Right. So the final goal is computation. We want to support two models, log and weight versus backfill. Log and weight is like when you first begin a dummy inference of sorts, so you don't use the feature, but you're serving it online and logging it, and you wait for enough data to work in it. So if your business is seasonal, you cannot really afford to do this. You'll have to like wait for a year to accumulate enough data to train a good model that handles seasonality. The other one is backfill. So given that you have all the raw data already, like if you have all the raw data in your warehouse already, you can derive all the features in history without having to wait. Right. And the next goal is real-time features. So real-time features are extremely powerful in different areas like customer support, search recommendations, fraud detection. They are just like have been super useful and super important for a lot of modeling use cases. And it's one of the core goals of Chronon to support this as a personal system. Right. It's also one of the hardest system problem in the world. Like we're asking data scientists to write stream processing systems, work with storage engines, which is definitely not the right fit. We want to abstract that away from data scientists and like help them focus just on the modeling part and feature engineering. Right. So this is hard because what I said earlier, you need to figure out stream processing, scale batch processing, work with storage and latency optimization. All of this is a burden that we want to like incorporate into the feature engineering platform and like abstract it from data scientists. Right. So non-goals of feature platform. So feature platform doesn't do model training or inference. That's a model management platform. Something like MLflow is a good example. And this system, although it has been used for generating business reports and like all other non-ML style use cases, but it's not really suitable for interactive report generation kind of use case or business intelligence kind of use cases. So what I'm talking about is that there is a divide in processing engines, right? If you might have heard of Spark and ClickHouse or Druid or like all this other stuff. So Spark is really for scaling over a large amount of data. And ClickHouse is like you take a small amount of data, but you try to get the results very quickly. Spark is slower, but much more scalable. ClickHouse is a lot faster, but not as scalable. Right. So we are more in the Spark camp. You know what features you want to compute, you just express them, and you're okay with waiting for hours for those features to be back. Right. Now, that's what I mean by static usage. It's that you can like write and wait for a while instead of like trying to use it interactively. So those are the two like big non-goals of Chronon. Right. So requirements. So we have basically 5 systems here that we build Chronon on top of. First one is Kafka, can condense all your events, and Hive or any other batch catalog. And then you have Spark, which can run the computation. So Zipline expresses all the algorithms that it uses to compute features as Spark topology, as Spark jobs. So you need a Spark cluster essentially that can talk to Hive or Kafka. Right. And the last two things are like first thing is like key value store. To serve online inferences, you need to get your own key value store. It can be anything like Cassandra, HBase, Redis. It's just an API from Chronon point of view. As long as you implement the get put bulk put API, you can use any key value store. Right. And the last thing is Airflow or any scheduler that can schedule pipelines automatically. So we have an implementation that works with this particular setup. So now going a bit deeper into the problem statement. So let's say you're trying to recommend items on something like Amazon, right? And you have certain users, and at certain timestamps, we are like looking for features for these users. Right. And one of the features, let's say, is view count of a user in the last 5 hours, whether this user has been active or not. Right. So there is a view stream data. It comes in as events to Kafka, lands in Hive somewhere. right? And the next feature is average rating of an item in the last 90 days. So the previous feature was about the user. This feature is about the item, right? We want to know what is the most recent or like recentish rating of an item because we don't care like, what is the rating a couple of years ago, right? And just for the sake of this argument, assume that ratings is a database table, so that people come in, write their ratings, give a number rating also, and that can change over time. People can come and update that rating. So as those updates happen, we still want to like maintain this view of average rating in the last 90 days. So what Zipline needs to do offline is look at that source data and enrich the input, enrich your list of like user ID and timestamps with all the features, right? And online, it's the same thing. We need to produce the same values. So if you were to ask for Alice's features at this point in time, you need to respond with the results. So that is essentially the simplified problem statement. Right now, just to visualize what's happening with the source data, right? There is a timeline, and you want to like make a prediction at the point in time. So going back, this is the timeline, right? This timeline is represented as this timestamp column. Right now, we have a label at a later point in time, which tells us if Alice made a purchase or not. Right, and then there is two data sources. There is a view source, and then there is a rating source. And we want to compute the windowed aggregation of either the view or the rating, right? And at another point in time, we want to like make sure we are refreshing the features and creating newer or fresher features to power the recommendations, right? And what needs to happen is that we need to backfill first. We need to create this training data first before we can do any of these other things. Right? Either we log these and wait, or we backfill these things. So that's where like backfill becomes really crucial. We need to generate this view before we actually begin serving. But serving is useful to like show you how to think about it. All right. So yeah, the example is an e-commerce platform, and just to expand the example a little bit, we are counting item use of a user in the last 5 hours. So this is coming from item use stream. So the underlying things are basically parameters, right? Similarly, average rating of an item in the last 90 days from rating scale. So here count or average are aggregation operations. The inputs are item use or ratings, right? And the key is either user or item. And aggregation window is like how many days or how many hours in the past you want to gather the data. Right. So these are essentially the parameters for group by. We talked about the group by concept, right? So we can give these as the inputs to the group by, and we'll figure out how to generate the stream processing jobs, how to generate the backfill jobs, how to serve these features in low latency. Right. All of that is powered by this configuration essentially. Right. And you can also toggle accuracy. So you can choose to enable real-time accuracy, power it through event streams like Kafka. Or if you don't have the Kafka stream and if you just have high tables, you can use daily accuracy. Right. So going a bit deeper into data sources, I'm just going to lay out a typical setup of where data comes from, how it like flows through various systems in the company. So you have a service fleet that serves application traffic. So you go to Amazon.com, some services serving your requests. Right. And there is a production database which powers those requests. So Amazon is pulling data for items about you and surfacing it through the browser. Right. That's coming from the production database. Now, this data goes into an event stream from the service. So your clicks, your views, everything like goes into event stream, and even gets accumulated in the offline data store like Hive. Right. And similarly, the production database gets its changes streamed through the event stream, and it gets captured offline. And additionally, like most companies have this snapshotting mechanism where, like at the end of the day, every day you take a snapshot of the database table, right? And then there is other kinds of data, which is derived data. They don't have any real time or like Kafka component. They're just data hive tables that get materialized every day through other processes. Then there is media. Media is things like images or audio or video, right? So there is essentially groups of sources which contain the same data. The event stream and event log obviously contain the same data, and the change stream and the database snapshot and the change log, they also all contain equivalent data. So that makes a source. A source in Chronon is not just a single box here. It is a group of these data elements that represent the same data artifact. Right. And lastly, we have derived data. So this could be like fact tables or dim tables that are computed by other tables. Right. And then there is media. So media is audio, video kind of stuff. It doesn't need explicit support from Chronon. Right, you probably want to generate embeddings off of this media data, and you can use Chronon to manage the embeddings. But we explicitly don't operate on media data. Right. So there is so if you remember, there is two or three kinds of data sources essentially. The first one is events, so it's clicks, views, etc., or like bank transactions, things like that. And the way to determine if your data source is event or not is that if the partition in Hive contains only the events that happen that day. So each partition only contains events happening during that day. Right. So fact sources are basically event sources too. So facts also are model type, but dim sources are not events. Right. So we can get point in time correctness just with this Hive data. So you can say any feature based on this data at any point in time is computable just using this. Right. And if you want to serve online, you also need a Kafka topic, basically. Here is a simple example. I won't spend too much time on this, but we are basically, it follows that schema I was mentioning. So 920 has only 920's data, and they all have a notion of a timestamp. This is pretty important. So this is what we use to roll back features to different points in time. Right. And similarly, the other thing is entities. So this essentially is DB snapshot or DIM tables. You can use tools like Scoop to populate DB snapshots, or you can use. What is special about this is that we can also support change data capture. So if you are capturing change data through bin logs, you can use Chronon to roll back your database table to a specific point in time and derive features on top. Right? You can use things like Debezium, which runs on top of Kafka to do this. Right. So we get point in time accuracy for this data by using the snapshots and the mutations. Right. And we also generate those real-time refreshed views using the snapshot table and mutation. But the key thing is that, if you have CDC, you get point in time correctness. If you don't have CDC, it's going to be daily correct. Right. So here is an example. So we have a snapshot of data, basically of reviews at a particular date, and at the next date we have like another snapshot, and basically there are some mutations to this table so that it became this table. So these are the mutations. So it says this is the old version and this is the new version. You can express your filtering and transformation logic as Spark SQL statements. We think Spark SQL is like extremely powerful, so there's no need to reinvent the wheel here. And we capture those different elements in a single event source. And you can specify keys and windows and aggregations. So this is like how you declaratively specify. And this generates three things: the backfills. So backfill is like training data for offline training, and online serving features. So it will expose an endpoint where you can fetch these things in real time. And lastly, the data quality metrics for the features that are being pulled from Google. right? So going down to the architecture, right? So here is what it roughly looks like. You write your Python code as like a config and use this compile.py to generate a compiled version of this thing that the data pipelines can use to generate uh, all the downstream jobs, right? So there are like 4 kinds of jobs essentially. There is backfill, quality, batch refresh, and streaming refresh, right? And the client basically is consuming from key value store. And one of the big goals here is to reduce the latency to be sub 10 milliseconds for each of the inference requests. So all of this is on Spark and Airflow. This is the rough architecture of Chronon. I'm going to stop here.